Greetings. It gives me great pleasure to be here in Amsterdam virtually. To be honest, I'd rather be physically in Amsterdam, but sometimes we don't get everything we wish, and we have to make the best of it. In a way, that's sort of a theme of my talk. If I had my wishes, all the data that I need to work with would be available in clean, well-tagged, semantically nice XML, but it's not. And that is where Invisible XML and Aparecium come in. I'm here today to talk to you about Aparecium, which is an XQuery and eventually also, I hope, XSLT library for Invisible XML. I'll talk a little bit about what Invisible XML and Aparecium are at a very general level, talk about how to use Aparecium, and then, time permitting, spend a little time on technical issues and next steps. What is Invisible XML? Well, Steven Pemberton brought the idea up at Balisage in 2013. It is a method for treating non-XML documents as if they were XML. It combines two really important ideas. The idea fundamental to XML and SGML and descriptive markup in general, that documents have structure worth exposing to software, and not just documents, but information of any kind. And non-XML resources, even though they have often implicit structure, even though it's not made explicit with markup. Invisible XML allows us to get access to that implicit structure by making it explicit, by parsing the resources using appropriate grammars. So it serves two audiences. One, it allows authors to work in non-XML notations if they prefer. And second, it allows people working with the XML toolchain to read and process non-XML resources. Take, for example, the example of natural language. The sentence, "Sarah laughed," will be described by almost any linguist as consisting of a noun phrase and a verb phrase and final punctuation in the written form. The noun phrase consists, in this case, of a personal noun, Sarah, and the verb phrase consists simply of an intransitive verb, laughed. A more complicated sentence, like "the cows on the hill ate grass," will have a more complicated internal structure. But if you have a grammar for English that understands this sentence, or a fragment of English that understands this sentence, you can get that structure out. Now, that parse tree is a tree structure, and so it's natural to represent it in XML. This is the same parse tree. This is the parse tree produced by Aparecium when given that sentence with an appropriate grammar of English. Natural language is a nice example, although natural language in its full extent is rather complicated. Artificial languages are maybe an easier move. I write CSS more or less conventionally, but when I process it, I would much rather have it in an XML format, like this one, again, produced by parsing the example at the top with an appropriate grammar. So much for Invisible XML. Now let's talk a little bit about Aparecium. The name Aparecium comes from the Harry Potter novels. Some of you will remember vaguely. Some of you who have read them many times, perhaps with children, will remember it very clearly. Hermione suspects that a book contains invisible ink, and so she uses a spell called Aparecium to make what is invisible visible. Aparecium is a proof of concept implementation of Invisible XML. It's for use in XSLT and XQuery, although at the moment it's available only for XQuery. The XSLT version will come along soon, I hope. And the basic idea is to provide a function that's like the doc function, except that I can use it for non-XML data. Or equivalently, like the unparsed data function, only instead of returning a string, it returns a document with the structure of the information. The easiest way to learn about invisible XML is probably by example. So I'm going to shift over into Oxygen and show you a simple example. I'm not going to show you the entire file. The critical bit is the demo element in the middle. It's an XQuery module with some literal XML. As the text says, this is a small demo of using ixml from inside an interactive XQuery interface. We can evaluate the query to see the result of parsing this grammar, using that grammar to parse that input. It will take a moment, but we can click the button. It will evaluate, it will look at, parse the grammar, understand the structure of the grammar, construct a parser for the data, and produce, well, this is a grammar basically for S expressions. We're going to produce a list, and a list consists of an open paren followed by a sequence of items, 0 or more items separated by S's, which is my convention for space, followed by a closed paren. The minuses before the literals indicate I don't want to see that in the parsed output. An item is in turn another list or a sequence of digits, and space is either a comma followed by white space or just white space. And again, I don't want to see it. You can see the character classes here include Unicode character classes. This covers all of Unicode space characters, and we can change this if we like and parse it again. And we will get any moment now a different structure. We can change the grammar to make the parens visible. This is the first form of the grammar that I wrote. And it's from looking at the output of parsing with this grammar that has all of these literal parens and so forth that reminded me I really want to make those invisible. Okay, back to the slides. Wrong. Apologies. You could also do arithmetic expressions. Some notes about Aparecium. As you can tell from the response time, perhaps, it's a proof of concept, not industrial strength code. It's really kind of slow. And it's not terribly well debugged. I'm not an industrial programmer. Next, how do you use it? How do those demos work? Well, of course, the prerequisites are that you have an XQuery engine, some input, and a grammar. And to use Aparecium, you import the module, you read the grammar in the input, and you parse the string. Note, there are no restrictions on the grammars. Invisible XML specifies notation, but does not restrict the grammar. It doesn't need to be LL1 or LK or LAL1 or anything. It doesn't need to be unambiguous. If it is a syntactically legal context-free grammar, it is an acceptable ixml grammar. So let's look at those demos again. If we go up to the top of the demo, we see first a absolutely conventional import of module import in XQuery. We import a module defining the namespace Aparecium, give it a namespace name, and we specify a location. Then we initialize a literal XML element. That's just for convenience, because I figure everyone attending Declarative Amsterdam will be used to looking at XML in Oxygen. And then the core of the use is the rest of the XQuery module expression. We return a results element, and inside the result elements, we iterate over the test strings. We could specify more than one if we want. We iterate over the grammars. We could specify more than one grammar if we want. And then we call the function Aparecium parse string on that input and that grammar, producing output, which we assign to the variable O, and we return the report. And I've also got a little feature here. I can ask to see the parsed grammar so that you can inspect to see what grammar structure gets built for this input grammar. But I'm not going to show you that at the moment. Now, one complication may be occurring to you. We're getting the string we're getting the grammar in the form of a string, but we presumably need to build some internal memory structures to work with the grammar. And it seems wasteful to build them afresh every time we run the query for every input. So there's another way to do this. We iterate over the grammars, and for each grammar, first we compile the grammar from the string, and then we iterate over the test input strings. And instead of calling parse string, we call Aparecium parse string with compiled grammar and return the result. This allows you to reuse the compiled grammar. Some of you with long enough memories will think, oh, this is a little bit like compiling a SQL query. And that is exactly what it is like. Let's go back to the slides. I'd like to spend a little bit of time now talking about some of the technical issues, some of the internals of the parser and so forth. I'm going to give you a quick overview of early parsing and some of the issues that arise for Aparecium from the fact that Invisible XML uses an extended BNF notation, and talk a little bit about ambiguity and speed. Now, consider the task of parsing a string, like Sarah laughed, against a toy grammar for English. We have a sentence consisting of either a transitive sentence or an intransitive sentence. Transitive sentences are noun phrase followed by a transitive verb phrase followed by a full stop. Intransitive sentences are a noun phrase followed by an intransitive verb phrase, and so forth. Now, one way to parse it is to say, well, we want a sentence starting at offset 0, so look for a sentence. And if we look at the rule for sentence, we know that it's either a transitive sentence or an intransitive sentence, so we have a choice. Now, a lot of parsing technologies will require that we know which we want, that we be able to tell without looking further in the input whether what we are trying to parse is a transitive sentence or an intransitive sentence. Early parsing doesn't do that. It tries both. It says, oh, well, look to see, can we find a transitive sentence starting at 0? And also look to see whether we can find an intransitive sentence starting at 0. The rules for those, in turn, tell us that they begin with a noun phrase. So let's look for a noun phrase starting at offset 0, which leads us to say, let's look for a personal noun or a determiner or a noun or a pronoun, all starting at 0. And at this point, we're out of predictions. So far, we've had to look only at the grammar. And now the grammar tells us, well, look for any of Sam or Sarah or any other personal noun starting at 0. That's a concrete prediction. And we win. We found the word Sarah starting at offset 0. We also, we then say, oh, okay, that's a good personal noun, proper noun. That in turn constitutes a good noun phrase. So now we're halfway through the parsing of either an intransitive sentence or a transitive sentence. We're done with a noun phrase, and now we're looking for a verb phrase starting at offset 6. And we have some unfinished business. We also have reminders to look for the words the or some, a determiner, or a noun, or a pronoun at offset 0. None of those work. They all are dead ends. The only thing we're looking for now is a verb phrase starting at offset 6, and so forth. And so it goes. In a nutshell, early parsing amounts to trying everything that could possibly succeed. That differs from many parsing methods, which require that there only be one thing that can possibly succeed at any point. And early parsing differs from some other methods in that it tries nothing that is not known to be relevant. There are some general methods like CYK and some other methods which try everything, but they try it in a purely bottom-up way. And they end up doing a lot of work that is irrelevant because it could not possibly be part of a parse for the entire input against that grammar. Finally, Earley keeps track of everything it tries using what are called Earley items, which keep track of a range in the input, a from and a to, a rule in the grammar, and a position in the rule. And when you finally generate the Earley item for the offset 0 to the end of the string for the rule goal, and you have reached the state final in the goal, then you're done. And you can construct a tree from the set of items you've collected at some level in a purely declarative way. Early parsing is just the construction of a set that is closed under certain relations over Earley items. Now, ixml uses extended BNF. In a BNF, which is what Earley defined his parsing method for, the position is simple. It's a number from 0 to the length of the rule. We have two ways of dealing with the fact that early parsing is not defined for eBNF. We can compile the eBNF rules to a recursive BNF. That's a useful approach. Or we can extend the notion of rule position. Aparecium takes the second approach. Every rule in an ixml grammar has a regular expression on the right-hand side. Things can be marked optional, things can be marked as repeating, and so forth. Anna Brueggemann-Klein showed in 1993 how to make a finite state automaton from a regular expression in quadratic time. The states of the finite state automaton are the basic symbols of the regular expression, and to calculate how to interpret the regular expression as an automaton, she calculates sets of states that can be first or last in any given sub-expression, and what basic expressions can follow what other basic expressions. That makes up the transition function of the finite state automaton. So for the rule, expression is term followed by 0 or more occurrences of the sequence S, followed by addop, followed by S, followed by term. We get a finite state automaton that looks a little bit like the image shown here. Inside of Aparecium, we keep the rule and we just assign additional attributes to every sub-expression in the rule, working recursively and inductively until we finally have the entire FSA defined for the entire rule. And that allows us to assign a name to every state in the finite state automaton, and we can keep track of our position in the rule. It is the name of a state. Now, I said earlier that ixml allows any grammar. Doesn't need to be unambiguous. What happens if you parse an ambiguous sentence? The ixml spec says, well, you get a tree back, and it's anybody's guess which tree you're going to get. There's a signal that there are other trees. But I'm interested in the problem of ambiguity because I find that I occasionally commit ambiguity when I write grammars when I don't intend to. And when I find that one of my grammars allows ambiguous sentences, I would like to know a little bit more about it. So Aparecium wants in general to return all the trees that parse a given sentence. At this point, I think I'll go and show you. Let's not use oxygen this time. Let's use base X. In base X, I'm here looking at another version of this demo. This has the English grammar built in, and we're going to parse the three sentences. The cows on the hill ate grass, the cows ate the grass on the hill, and the cows ate the grass on the hill with the telescope. And we're going to demonstrate prepositional phrase attachment ambiguity. We seem to be done. You can see that the first sentence is unambiguous. The second sentence, however, is ambiguous. So Aparecium returns not one tree, but a forest of trees. First, first a transitive sentence with the cows ate the grass and they ate it on the hill, but also a second tree, the cows ate the grass. Which grass? The grass on the hill. And the cows ate the grass on the hill with the telescope, of course, is doubly and triply ambiguous, so it has even more trees. Unfortunately, some languages are infinitely ambiguous. If we have a simple grammar like this first one, A is either an A or the letter lowercase a, we have potentially unbounded numbers of trees, vertically infinite, so to speak. If, on the other hand, that is, you can have a lowercase a with inside a single A element, or inside, you can wrap that entire thing in another A element, or another one, or another, or another. And if S is 0 or more X's, and an X is either lowercase x or nothing, then the infinite string has, the empty string has an infinite number of parse trees, all of the same depth, but infinitely wide. Call it horizontal infinitude. Let's go back and look to see how that works here. I've modified these two grammars, but these are basically the two grammars I just showed you. And I'm going to test both grammars for a single input. And what it shows me, I hope this is large enough that you can see. For the first grammar, we get a single S containing an A, or an S containing an S containing an A. And at that point, Aparecium says, okay, that's a loop. We've been around the loop once. We're going to stop now. The second grammar gives us a similar situation. We've got two trees, one with a single X and one with two X's. And at that point, it says, again, detects that there was a loop and bails out. So you get some trees, but not all of them. Loop detection is one way to do ambiguity. If you're going to deal frequently with languages, with grammars that allow infinitely many parse trees for some sentences, it may be simpler to return a parse forest grammar, which is a grammatical representation of the set of possible parse trees. I won't go into detail about this. If you're interested, there's a very, very good discussion of parse forest grammars in Dick Kroene and Cyril Jacobs' book, Parsing Techniques. I've just shown you those demos, so we don't need to look at them now. Final question, the final observation I want to make is about speed and the representation of early items. I started by representing early items as elements, and then ultimately moved to representing them as maps, because all of the implementers I had talked to talked about how expensive it is to construct elements. And since early parsing creates a lot of early items, one early item for each character in the input, it seemed obvious that one of the reasons Aparecium was not as fast as I would like was that it was spending too much time constructing early items. Well, changing the representation of items from elements to maps improved runtime by 15 to 30%. I then measured and discovered that the major time cost was not constructing the early items, but finding them in the set of early items, at which point I changed the representation of the set from a sequence of items to a map of items, and that improved the runtime by a factor of 6 to 10. What now? What happens next? Well, the first thing is I should mention there is a past. There is related work. There's an invisible XML package in Perl, written by someone named Ed J. It doesn't use early parsing, and it doesn't guarantee the correct interpretation of grammars, but it's a nice idea. There's a functional parser for invisible XML by John Snelson. There are early parsers written in ABC, and soon, I hope, one in C by Steven Pemberton, and Thomas Hillman is working on a parser he calls JParser. There's other work, of course, related to parsing in XSLT and XQuery, the Rex tools by Gunter Rademacher and Dmitry Novichev's FXSLT LR1 parser. There's also some prior art connected to the exposure of non-XML resources in XML forms, that is, as if they were in XML, what some people have called XML lenses. Some of those have been commercial products, and some of them have been just ideas, like Simon St. Laurent's. What happens next for Aparecium is simple. I want to move from a proof of concept to a practical tool. I need to do some release engineering. I need to work on speed, and I need better error reporting and recovery. It would be nice to have a repository of grammars for standard notation, so we don't all have to write our own IXML grammars for CSS and JSON and XPath and XPointer and so forth. I have started working on a set of grammar analysis tools with the goal of being able to do some kinds of ambiguity testing and testing for whether the grammar is LL1 or LALR1. If a recursive descent parser is possible, it might be faster, so it might be nice to generate a recursive descent parser from an IXML grammar when that's possible and so forth. And then once the tools are in a slightly better shape, start building sample applications. That's it from me. Thank you very much. Are there any questions?